Mm.
Hey, hello, how are you?
Hi, kind of good. I woke up at 5 a.m. to do this interview, so I just woke up and ran to the computer. So let's do this.
Sure, no problem. So, can you please introduce yourself? You don't need to reveal your name, but I just want to know how many years of experience and what's your primary language?
Uh, alright. Um, I've been working for 3 years. I'm self-taught. I'm a web developer, so your database stuff, PHP, JavaScript, client and server. Uh, I'm interviewing for Amazon SD2 like next week, so I gotta do some system design. Yeah.
That's good. So, how is your coding skills? Are you doing the Amazon recently asked Amazon questions and
Yeah, so my coding is probably my best part. I do about 4 interview.io questions a week. Well, I interview other people. Yeah, my coding skills are probably my greatest asset, I guess, because I do a lot of these. I don't know. I think I'm good at it.
okay, that's good. That's good. So, sure. So let's jump to some system design problems. So, uh, I want you to design a system
Mhm.
which can give me a unique ID,
Oh, okay.
just the unique
Uh,
ID, and we can extend the requirements as we go through.
yeah.
Create a
Uh,
system which can generate a unique ID, and it has to
uh,
be and not just a single caller. It will be like distributed
yeah.
system. Okay. Okay.
Okay. So so let's create a system will give me unique ID. So uh, distributed system that gives unique ID. So the first thing, okay, distributed. So geographically distributed. So I'll write that down. Well, I mean, it doesn't have to be geographically distributed, but
So let's start with
yeah.
generating a unique ID, and then we can extend the requirements towards that.
Okay. So yeah, unique ID. No one's allowed to have the same one. My first, I mean, the simplest thing to do if it wasn't distributed is have a single counter, and whoever asks for a counter, and the counter is an atomic value, and whoever asks for the counter, just locks it. I guess it's an atomic value, you don't lock it, but you increment it and go home. You increment it, take it, and go home. So that's the easiest way to generate a unique ID. So I should ask, like, this unique ID, is it being called by internal API? So is the unique, I'm going to call a unique ID service being called by clients? Is it being called by sort of internal services? Is it by, I think this affects my answer. So,
Okay. So it will be called by the clients. So clients will be calling our service
yeah.
to have a unique ID.
Okay. Um, so, okay. So first thing is, I guess we'll do first solution endpoint with atomic value with RS endpoint. So we'll go to get. There's an instruction which increments and also returns. So you returns the incremented value. And I don't remember what it is. I remember writing Golang a while ago. Yeah, this instruction. So value, that's the increment. And so it's an atomic. In this scenario, so you don't have to lock it.
So what do you mean
So
atomic here? What is an atomic value? What do you mean here?
yeah. I'm just going to Google it because we got to this part of the giant system design book. So let's do it. Atomic counters. Yeah. Okay, so that's it.
Or do you think you have a table, right? Table in the background, and which will increase the counter, the primary key. They keep on increasing the counter, right? So you have the last ID.
Ah.
Okay, right? How about that?
Okay, so that's another. Okay, yeah. I'll finish my sentence about atomic. So it's a value that. Okay, it's a terrible idea for a distributed system. Okay. Atomic is a value that if there's multiple threads running in the same computer, if they both access it, they will not collide. So like an update instruction will not like collide with a read instruction. But okay,
Right.
I've been given a super big hint. Go with the table. Okay. Next solution. There is a table with a primary key. The same rest endpoint increments the, or no, inserts record and is given the auto increment key. So wait a minute, this is the table. Oh, sorry. Yeah. There's an advantage to this one.
I'm sorry. I'm actually trying to ask you about the disadvantages of this solution and also this approach.
Okay, so yeah, cool. I can totally say that because I just found one. So disadvantages, atomic values, multi-thread environment, not a multi. I'm going to call it node container.
Not distributed, right?
Yeah, environment. Okay, I guess that's what that word means. So yeah, I mean, as soon as I get more than one CPU, I'm out of luck. This is a pretty solution. It's I guess I'll put this in advantages. No, I don't. Do I need that? I mean, one thing that I noticed in this one, I can insert metadata into for more detailed history of that. For more detailed history of that. So one thing that I noticed in this solution, it's like logging is kind of built in because I'm inserting record anyway, so I guess I can put more stuff in that. IDs,
okay.
What they got. Disadvantages, let's see. So my relational database fundamentals are pretty fundamental. I don't know how something like Aurora or a distributed like MySQL services handle this.
No, this is just a simple table, right? A simple table.
Yeah.
It will have a auto increment primary key. It will keep on returning the primary key. But how long it will return? You have maybe say 1 trillion calls, right?
Yeah.
So how can it scale? It can handle the load. That's the first thing, right?
Okay.
So the auto increment, it may end at some point. It cannot give you like unlimited, right? So that's the disadvantage.
Okay, so that's a question I haven't asked yet. What is the scale? What is the scale? Like, I mean, you said a trillion requests for it. What is the load of this service? I think it's load or requests per second, day, month kind of deal.
Okay, so that's when I recommend you to follow some template. So why don't you create the functional requirement? non-functional requirements. Functional requirements is all of
okay.
this,
Yeah.
right? A non-functional is, hey, do you want me to, have my system available 24/7, durability, fault tolerance, right? And how many calls per second, right? And how about backup envelope calculations? So I'm gonna put some annotations for you, okay? So, but yeah, please go ahead. That's fine.
Wait, so functional requirements and non-functional requirements. Cool. So yeah, so non-functional requirements is like reliability. Does or what kind of thing? I guess I'm going to put the words, how often does this service, or no, I'm trying to formulate. So I could say, what kind of bad things have, no, it's a requirement. So yeah, how often, how much does, what are the uptime requirements of this service? So 24/7, 99%, 9.9% kind of deal.
Excellent, good.
With
So talk about 99.9, 99.9. So you know this theory, right?
Yeah.
5949.
Yeah.
Okay, good.
Okay, yeah. So I know the theory, but I'm thinking, how does it apply to like whether I use like which relational database or, yeah, because for example, if I ran out of a sequence, if I had that many calls and I had a sequence and it's hit the end, what would my relational database do? It would just crash. Maybe I could roll over the IDs. That may be a manual thing on my end, so I may have a service that would like just roll the IDs forward. Let's see. How long does it take to create a new table in like, I don't know, Postgres? Not very long, actually. So that could be, at this point, my IDs are no longer unique. So that's a disadvantage. And I know like in Aurora, like MySQL's distributed platform, you commit to an append-only log and it's distributed, and eventually you commit. So how long does that, what's it called, the write-ahead log compaction take? And does it affect the inserting time? I have no idea. So that's what I'm thinking.
We can ignore that for a while, but so let's think about this, right? Request per second, non-functional requirements. Okay, so maybe 1,000 requests per second, right? Let's think. Yeah,
1,000 per second.
requests. Yes. Or let's put it simple. Okay, just 100. Say 100 per second.
Okay, 100%. Okay. So so there's my non-functional requirements. And I go back and I say, or disadvantages. Cool. Okay, so I'm going to move down to line 35. So a disadvantage I can think of is, with 100 requests per second, we'll just say MySQL biggest. A big int is 8 bytes, so which is a really big number. So if MySQL big int, I'm assuming there's corresponding types for other database, you can store 8 bytes. So 8 bytes of an int, which is 8 part 8, right? Yes. Part 2. Yeah. So what this means, this is a huge number. With 100 requests per second, okay, I'm assuming 8, 5, 8, power 2, a huge number. So there's 57 zeros, 57 zeros. So actually, I'm going to put that in my.
That's fine. You don't need to go into the detail, but
Yeah.
just tell me what's the disadvantage of having a table.
Yeah. Yeah, that's kind of just a note, so I'll put that up there. The disadvantage is I think it's a little bit storage overhead. I don't actually need that record, assuming I can forego logging and stuff like that. When I'm super performant, I don't need the table record. I don't need the table record. The sequence may run out. That's 2 points actually. So I don't need a table record.
So what do you mean you don't need the?
Like if I'm inserting records into a table, now I have a table filled with stuff I don't want, or I don't need anymore.
But you have like only.
Yeah, it's like maybe one. Well, it's 8 bytes. So it's an 8-byte record.
Okay. So you're saying that, let's say, if you generate a number 2, but you are using 8 bytes just for 2.
Yeah.
Is that what you mean? Okay, cool.
Yeah, and then eventually, if I have like a million of those, I'll have 8 million bytes, which is not that bad. So
right. So let's say, if you want to have this as a distributed, right? So which means only one table, you will, like, multiple callers will be calling this only table, right? That will be a lot of right, a lot of latency. And the other thing is, so let's write that point here. So distributed environment, right? May have latency. That's another thing. But let's say if you want to handle it by having a multiple tables, right? But you may end up in a duplicate.
Yeah. Right? Yeah, of course.
Okay, cool. Okay, all right. So, yep. What's the next solution? Yeah.
Okay. So, okay. So I have like another key idea. So I can keep with the table concept, or I don't have to. So when you said, yeah, you may run into duplicates multiple tables, I just realized like my integer range for the big integer is like 8 by 8 by 2. I can, if I want, I can have multiple tables. So I guess we'll have a next solution. Next solution. I think this merits a next solution. Maybe I should just put in that. But multiple tables, each with an integer range, or I guess an integer range. So it's a multiple. Do I need multiple relational databases? I mean, I'm just going to say it. Multiple tables, each responsible for a range of integers. Okay, so in the same fashion, same rest. So the same resting points is given the auto increment. Multiple tables. So disadvantages. So with big points per integer, can, let's see, 8 bytes per integer. Yeah, I can give, let me do some math on the, so 100 times 60. I'm going to do the math on the request per second so I can like estimate orders of magnitude. So I have.
Okay.
Cool. Okay. Okay, so now I have another question. How long is this service expected to be up? Is it like forever? Is it like a year? Is it like maybe a month?
Okay, so say 30 years.
Okay, 30 years. 30 years, and then 3,000 times 3 series. 30. All right, so napkin math calculations. It's not a huge number. So, so this is the expected. However, it's not like, so, okay, so I have another question. What is my, there's a word for this, I don't remember it, but so I could have, you say 100 requests per second. This seems like kind of reasonable. What is my like range for estimation? So like, do some days I get 200 per second? Do some days I only get 50? What is my like upper bound for requests per second instead of, or was that the upper bound? So is 100 per second the sort of maximum request I'll get, or will it fluctuate? And will I have like 200?
That's the max. That is the max.
Okay,
right.
So my total expected apparently comes to 94 million. You know, we don't have to, we can be,
right.
we can overestimate that.
So it's for 30 years, right?
Yeah.
So let's put it this way, right? So, yeah, you don't need the exact calculations, but just,
but
you know, you can just come up with, hey, you know, maybe I need a 1 billion or something, right?
Yeah.
So yes, 94 million or you know, 1 billion. So you need for 30
94
years.
billion.
Okay.
No, it's 94 billion. That's
94 billion. Okay, so 94 billion, right? So or 1 trillion or anything. So come up with that number. That's fine, but
So it's roughly 1 trillion. So I'll just bulk. No,
okay.
well, 500 billion.
Okay, that's good. So
so
that's
if I
what
go
you
back
get in 30 years. So do you think whatever the solutions that you provided just now, the table, atomic value, or anything, do you think that will work for this number?
For this number, yes, because the big int is well within range of that. The big int has 57 zeros. I mean, maybe like an unsigned big int has a huge number range.
Okay.
So for example, if we're being very obsessive, so divide up the integer a lot. So yeah. Yeah, that's a huge number. All right, so let's say I have each. I wish I could describe that number of things. So let's say, for example, each table gets their incrementer set at 1 trillion. So this is like similar to it's not really a circular, or it's like consistent hashing maybe. So T1 gets like 0 to 1 T, and then T2 gets 1 to 2 T, T3 2 to 3.
Okay, so let's think. Okay, so let's think just the solutions that what we have right now, either a table, right, having a multiple table, right, the solutions that we have right now that may not work for our service. Let's say if I increase from 100 per second to 1000 per second or 2000 per second, it's not going to work, right? Or
Yeah.
maybe 10,000 per second. So let's come up with something,
Okay. That's
some other approach.
agnostic. Yeah, it can scale better. Okay.
Right.
So if does not scale, eventually does not scale. Okay. So what other solutions do we have for? So should I keep going with, I have a database with records, or can I now design my own auto increment key? Like,
Yes, I want you to go with the second.
Okay. Next solution. Next solution. Okay. So, so with the relational database thing, I had 8 bytes per row, which meant that if I had, let's say, if we ended up scaling this to 1,000 per second, I mean, that would just, oh God, that math is not amenable to me this morning. But are the storage costs negligible? All right, so 1 trillion bytes.
So think about this. Do you think you can return the timestamp, epoch time? Do you think you can return the epoch time?
I don't think so. So second since 1970, that would mean that 2 people who requested the same second, which there are roughly 100 of it in this scenario, I can't return the timestamp. Could I return a more precise timestamp, like nanoseconds?
Okay.
Depending on my frequency. So solution, return the time value. So we'll do advantages. I guess the advantage is that a lot of almost all programming languages have precise time libraries. You need to implement this. So I'm going to do an order of magnitude disadvantages calculation. So like I need a really precise time function to scale, and even then there is a non-zero probability that multiple nodes may be same time.
Okay. So think about it, like how can you avoid that?
Yeah,
right?
so
How can you handle those disadvantages?
okay, so I need a really precise time function. Is there hardware to do this? Is that part of this question? Is there like time hardware?
Not a hardware.
But like, yeah, there's computer functions that.
So some small. Let's think about like some small tweak that can actually handle this problem, right? So it's a simple. You create a a timestamp, but including timestamp, you will also do something else, right?
Okay,
Multiple
so
users will be calling it. Why don't you have concatenate with the user or something?
Yeah. So I could append user-specific information or a hash value or a geographic key. So like basically each host could be given a key. Okay. So solution, return a time value with and a hash and another value unique to the, should I say, node and user. So like basically, so it's like timestamp, node hash, user hash. So this means in order to even have the probability of generating a unique key, that the user has to do 2 requests at the exact same time to the same server.
Okay.
Is that acceptable? Like,
Oh yeah, definitely.
yeah, okay. All right.
Right. So the same, say, think about like the same user can call your service multiple times at the same second. So how can you handle that?
Great. How does they handle? I mean, I can implement some sort of queue, like per user queue, but that sounds awful. So the same, yeah, I could basically say like, here's a queue of like this many times user called this, dispense IDs one at a time. That sounds awful. So how do I mean, I could have a vector clock in the back. Per node, you could have per node. There is also a vector clock is incremented for each ID.
Excellent.
So
Yes.
if I have a vector clock, I don't need the rest. I'm assuming,
So what do you mean each ID?
or for each request. Sorry.
Each request for a user ID?
Yeah, so like, no, just for a unique ID. So like every time you want a unique ID, I increment the vector clock, and then append that number to the end of the timestamp. So like I know, yeah, it just basically makes the timestamp unique.
Okay. So do you want to write one example for me?
Okay, so hope is a notation for so request. Okay, to V is one request. So make this timestamp 1. Well, 2, 3.
Okay. So
Yeah. So this is my unique ID.
right. So my other question is, this this you were going to use the vector clock if it is at the same nanosecond, right?
So checking at the same nanosecond, I think is
Think about this, right? So you have 1, 2, 3, 4, 5, 6. So this is your maybe 3, 4, 5, 6, 7, 8,
yeah. Like,
9.
why do we need the vector clock? Why do we need the timestamp if we have the vector clock?
Oh no, I'm not asking that. So you see, at this at the same timestamp, you could get multiple calls.
Yeah.
Then you are going to use this vector clock. Am I right?
Yes, I was going to use it for all of them, but in retrospect, yes, it makes sense to use them for the same timestamp. So
exactly right.
Yeah.
So there is no use of like for different timestamps because different timestamps are different unique IDs, right? Okay,
Yeah.
that's good. Okay, that's what I want to know. So that's what you want to know. Which I mean, so you came up with multiple ideas here. So the first thing first, right? So I'm going to a little right here. So, okay. So the first thing is you said timestamp plus user ID, right? This is the first thing, and the next thing you came up with is timestamp. Oh, sorry. Why? Okay, timestamp plus user ID. And the next one is timestamp plus user ID plus user IP address or something, right?
Yeah.
This is another one, and the third one is user ID plus user IP address, and this one, right? So this is what you want to do.
Yep.
Value plus. Okay, this is good. So this is what I'm looking for. So you will try to maintain some vector clock, or when if it's at the same time timestamp, then you're gonna simply increase it, right? So let's okay. So I think we are almost like 35 minutes. So let's. So now I'm agree with this solution. Okay, so now I want you to design the detailed design. I want you to handle. Let's see how can you scale it and everything. So let's just move forward. Yes.
Okay. So okay. So design the specific service. So, so kind of, all right. So I have. So is this part where I use like a diagram sort of deal? Like.
Yes.
Okay. So we have REST API. Get. So I know there are faster ways to do this, but I'm not. Yeah, I should totally Google those. But currently, I'm a web developer, and all I know is my HTTP verb. So we'll do get unique ID. So here we can have a load balancer. So we can go to a load balancer, and then to like one of many. Like one of many services, basically. This is kind of slow because this is kind of slow because it's like basically we all have to go through the same thing, maybe. It means I'm thinking we have one monolithic load balancer and all the requests go through that. But do we need a load balancer for our application, or is it like we've designed something that doesn't need one? I'm going to say that don't need a load balancer.
Why you don't need a load balancer?
I guess because in my mind this is distributed. So, because this is distributed, so it's geographical. Many users can call the same API at the same time, but is this correct? Time without issue. But do I need it for example, other reasons? Like, I don't want one of my data centers being the only hot one. Okay, maybe. Okay. All right. I will. Maybe I do it to distribute network. Okay, so I will use the load balancer. All right. So we have my load balancer, and then we have actually. I'm trying to think of. So I have a scale. So at this point, I want to say per continent. So
what type of load balancer you're talking about? There are software, hardware, L4, L7, right? So what type of load balancer?
I don't know what those words mean because I have not. But when I think load balancer, I'm like, what is it called when your load balancer just simply has 4 services? So like you have 4 services, S1, call it ID Gen 1. So it just ID Gen 2. Cool. So this is like, yeah. So it just picks between them. No, it doesn't pick. It just has it does do ID Gen 1, do ID Gen 2, do ID Gen 3. Like it just evenly distributes it. Yeah, it doesn't analyze the traffic. It just splits a request between 3 different nodes. That's the type of load balancer. I don't know the name for it.
Okay.
So we have. Okay, so here's another question. So I can have one load balancer global, or can I have one per continent. So everyone's going to call. Any rational actor would call the load balancer on their continent, because this is good. So I can assume that, right? One load per continent. So this is like geographically spreading, I guess.
But don't you think that's the single point of failure if you have only one?
Okay, yeah. Okay.
Okay, that's fine. But you know, right?
Yeah.
So you know how to handle it. So maybe you want to have another one which is an active passive or active active, right?
Yeah.
So that's good. So Maybe not. Don't include that count. Or maybe I need
Yeah.
two load balancers or something. But just say I have another set of load balancers in the background, which it can be one active, one passive, or something like that, right? Yes, exactly. So to
And
handle the
load
single point of failure, right?
Yeah, and backup in
Good.
case of failure. Okay. So then I'll connect my diagram here. All right. So I think.
So you have a client.
Hmm?
Client will call the get request. So what exactly will happen? So don't you think it will go to the nearest, the DNS, and DNS will resolve? So I want the complete structure. Can you do that for me?
Okay. So then there's something in front of the get request basically. Where's this diagram?
There is a draw section. You can actually use the draw section here.
Okay. Let's see. So yeah, I'm still in HTTP land. So how is DNS going to resolve my service? Okay. So we'll have. I'm going to use the A. How big is it? So we have continent1.dns, continent2.dns, or yeah, whatever. So my idea is that we'll have a continent1, continent2, or some other geographical distribution of DNS records, and that will point you to the getter continent1.com, continent2.com.
I don't want to know the detail about the DNS. I just want to know, okay, the request comes from the client, it goes to the nearest DNS, and nearest DNS will resolve the IP address, it will goes to the load balancer, right? So I just want that, some detailed diagram. That's it. Yeah, as simple as that, because we have to concentrate on scaling in later service, not here, right?
Okay, so yeah, each DNS is to a specific load balancer, which has 3 nodes, which Gen 1, Gen 2, Gen. So each load balancer has n nodes, I guess we'll call it. Yeah. So that's the architecture of that, I guess, for now. I guess I come over here. Make it a bit smaller. Okay. There's the architecture of the request. So you have your client sends a get request to continent 1, 2, or 3. The DNS resolves to the IP of a load balancer. So now we're the load balancer. The load balancer will distribute all requests evenly. I don't know what the word is, but to each node. The node itself will have. Okay, so. How do I do this? So we'll draw a node. Not connected to call, strange.
No, it's me. I kind of connected from the other iPad. I just wanna, yeah.
Cool. No, I made it too small.
Okay, so let me put this. Are you writing something? Because I'm not able to see.
No, I'm good. That's good.
Oh, sorry. So let me. So you said here is your client, right?
Yep.
Client will make a connection. Here is your DNS resolver, right?
Yep.
And here is your load balancer. and you have a backup of load balancers here, right?
Yep.
And from here, you have all of your services distributed, right? Your web services, right? So
Yep.
it's maybe for a scalability issue, you can have like, all are deployed as a microservices in somewhere in the AWS, right?
Yep.
So you're gonna call this as S1, S2, S3, S4, right?
Mm-hmm.
And here is the algorithm that whatever you just prepared right now.
Yep.
So that is your how can I do this? Maybe you can call that as the KGS, right? Key generation service,
Okay.
which is
Yeah.
call this, right? So what are the single points of failure at this point? KGS.
Okay. Yes,
Right?
KGS
So obviously
is
you have only one, so you can have
Yep.
repeat objects, right?
Yep.
That's it. So this is the small diagram, and
Okay.
right? Yeah. So
Yep.
I want you to draw this. You don't have to worry about it. Yeah, exactly.
Mm.
Yeah. Please continue now.
So draw.
Or you can erase this if you want.
Yeah. All right. So I know it's multiple KGS. So yeah, we have multiple key generation services. So what I want to do now is like sort of elaborate internally how it works. So how the key generation service works internally, where it assigns you an ID or a timestamp, and it holds in memory that timestamp for, let's say, for some amount of time with its associated vector clock. Is that the stage where I should move? Because the diagram is roughly drawn already. So now I'm elaborating like the KGS. So the KG.
So I'm sorry. What is your name, by the way?
Oh, my name is Marvin.
Marvin, right? So let's think about this. Come to the draw one. So I want to let you know. I'm going to tell you one another thing here. So in this diagram, right? So you have a KGS, right? So think about like KGS is single point of failure. Okay. So what can you, if I want you to ask you about the latency, right? What can you do so that it will have a minimal latency?
What can I do?
Right.
What is the source of? I'm trying to think. What is the sort of source of latency now? So, I mean, we can have better geographic distributed services. So right now we don't have any locks.
Right.
It seems pretty quickly. So the key generation service is performance. So there's the optimization
right?
made.
So you have the vector clock, you have the epoch timestamp. So you said vector clock you can have increase that counter until 500 maybe, and then when it goes to a new nanosecond, you're gonna reset the counter. Again, it will start from 0, right? So so you already had that basic algorithm. So what I'm thinking is, so do you think you can add the cache layer here, right?
Can I add a cache?
Yeah, definitely, right?
To which service? Because like it's an ID service, so I can't cache an ID. I need a new ID every time. What can I cache?
So now let's think about it. So now an interesting part, right? If you add cache, or why is there a need to add cache? Okay, so that's another thing. So before you call the KGS, let's think about this, right? So KGS will return, it will. So maybe I think I should draw something for you. So what I'm trying to explain is, okay, so it's a network call. Whenever your microservice, your S1 server calls the KGS, right? It's a network call that goes to KGS service, and KGS has to invoke whatever the method it has and then give back to you. So that's a network delay might happen, right? So if we use a Redis cache here, or some type of cache, Okay.
Hmm?
In
Yeah.
between your server S1 and KGS, okay,
Hmm?
what if your cache, you call for every thousand calls? Call your KGS for only every one in 1,000 calls. Okay. If you call one in every 1,000 calls, okay, maybe I'm gonna call and get all the thousand unique IDs from it and put it in your cache. Okay.
Oh.
You know what I mean?
Oh.
So
Yes, I completely forgot about this. Okay. Yeah. Just
exactly.
call.
So think about S1. S1 will do the same. S2 will do the same. S3 will do the same. S4 will do the same. So at the first call, right? S1, it will make a call. It will make a trip to KGS. It will get all the 1,000 and put it into its memory. S2 will do the same. S3 will do the same. S4 will do the same.
Yep.
But S1, until all of these 1,000 unique IDs are off, it will using the same in its own cache. So
Yeah.
let's say S1 went down. How many keys are you losing? 1,000 keys.
Uh.
It's nothing,
Yeah.
right?
One.
When you're talking about like trillions of keys, 1,000 keys is nothing.
Oh, I see. Oh. Okay. Yes. Thank you. I totally.
Uh-huh.
Yeah. Okay.
Right, right. Yeah, go ahead, please.
Well, no, I have nothing interesting to say. I did think of that. Now that I'm thinking of it, it seems. Yeah. So that's a way to do. We can cache the ID keys ahead of time and distribute them with like, yeah, an in-memory key value store. Okay. Yeah, so this is about the limits of my knowledge. It's 51 minutes. You can end it here because unless there are more things, this is super useful for me, by the way, but I am drawing a blank. Like when I see further optimizations, we can like, call keys ahead of time,
Right.
KGS ahead of time in cache. So I'm thinking, do I need to make this more distributed? Doesn't seem like it. Can I make it faster without like pre-generating keys? No. So to me, this looks like. I mean, I guess there are more trade-offs I could make. If this is a real interview, I would certainly try and make trade-offs. But even then, I'm struggling to think. How could I tweak the system for specific use cases? I don't currently know. No.
That's fine. So the thing is, right? So if you have in the real interview, right? So if you have a 45-minute or 50-minute interview,
Yep.
the only thing is you have to keep on talking, right? So keep like ask your own questions, right? Ask the questions, as many questions as you can. Try to find the faults in your own design, right? Try to find the faults in your own design and try to come up with a solution by resolving by yourself. Because designing a system, like complex system in 45 minutes, it's insane, right? But the thing is, the way you approach and the way you solve your own issues, that makes sense. I mean, that will make a lot of sense. So I'm gonna put out a review for you. That's fine. So let's come back to the diagram, right? So you have KGS service, you have all of these microservices are easily deployable, so it will take care of your load balancer will take care of. Oh, if it is deployed in the AWS, you don't need a load balancer to to on our side, right? That's another thing. Unless if you deploy it on our on-prem, then you need a load balancer. If you deploy it in the AWS or some kind of a storage, I mean, or Kubernetes or something, right? You don't need a load balancer because that's a cloud. So cloud will take care of the load balancing issues, right? Okay, so that's good. So let me maybe I'm going to erase this a little bit. Okay. So another question is, so what will happen after this, right? So the calls, it goes to the KGS.
Yeah.
So it will get the response. It will give back to the caller. That is good. So what can happen after this?
So service one, just service one. I guess I'll create a new color. So I think it's what's it's like the call goes from service one, and then it goes to the load balancer. It goes back,
Good.
back to the client. I guess.
So there is another thing here.
Okay.
Since it's a distributed, right? And we
Yep.
have a lot of the time, and we want this to be distributed like all around the globally, right? All around the world.
Hmm.
You're talking about taking a timestamp. What if, because people in Southeast Asia or Asian continent, and we have all of this time delay, right?
Hmm.
It's 12-hour time delay or 4-hour time delay when you are in the northeast region. When you are in central, you have one time, right? You are like 1 hour
And we just
behind, but
use what's it? Universal time? Yes.
hmm
GMT. We do our timestamps in GMT, of course. So I guess I can write that. GMT.
so wait, just a minute. So you may end up in duplicates when you have all of that, but you are saying that we can use only GMT.
So like the client doesn't actually care about the time. He only cares about the unique ID. So if we have geographically distributed computer centers, as long as they're still using like epoch time, they should be fine. Like as long as they're using only one time zone, the client doesn't actually care about the time zone, and the key generation service can make sure like all its distributed services never wait.
But you have
No.
multiple KGS deployed in multiple continents, right?
Oh yeah. So if
And
they're called the same nanosecond, it will not go well.
right. So how do you want to handle that?
I mean, reusing the okay, get rid of that big thing of text. So reusing the cache strategy, like to me, oh god, wrong color. Reusing the cache strategy to me now sounds really useful because we can have one KGS. Well, no, one KGS single point of failure, but we can have KGS with backups. Oh no. We can have so like a KGS service, and the KGS service, of course, has backups in case it goes down and has hot backups. But then we just have a bunch of Redis servers that are geographically distributed, which are continuously requesting keys from the original KGS, and that seems like an ideal architecture because we will never get repeats, but all of our clients around the world will always have the same. We'll always get a speedy response time, assuming nothing explodes or their rate of keys. So I guess we can have a. Why is my drawing tab is not having it? No, maybe. Okay. Yeah, my drawing tab has since decided not to cooperate. No. But yeah, so we just have a bunch of Redis servers around the world. Querying one KGS and caching the results over time. I think this is ideal because we never get key collisions. Is there anything wrong with it? For example, the rate of request goes up, the Redis service could run out. It doesn't seem too difficult to do a really high rate, or at least a varying rate. So if I detect that there are more keys or more requests coming in, I can increase the amount of keys that I currently have. Does that sound useful?
Okay. Okay. So, what are the other drawbacks with the?
What are the other drawbacks?
Uh-huh.
I guess the largest one is that if like too many people are requesting keys, then the Redis servers basically become slow because the KGS is not geographically distributed. It's in one place with one time. Yeah, so it's in one place. It has backups, so it will not go down for very long. But
so don't you think the Redis cluster can handle the load for you?
But if there are too many requests, then the Redis each node will run out of IDs, and we'll have to ask KGS. But I guess we can pre-cache pretty far ahead with that. So if we don't have to worry about that, then this architecture looks very good to me. Let's see, what are problems with it? I don't know. Let's see, problems with it. Our single point of failure is obviously are like 1 KGS, but if we make backups for that, so we have our KGS, I don't know, like in Europe somewhere. Yeah, we have backups for it. Every Redis server, one in North America, one in South America or something, will ask the KGS for IDs and distribute them quickly. That's trying to poke holes in my own design, solve its own problems. Is it fast? I think so, because you're pre-caching IDs. Is it reliable? We can make backups for KGS. We can have failover Redis servers, stuff like that. Is it performant? The KGS itself is quite performant. Redis is quite performant. The only point of failure that doesn't involve backups or failures is the fact that too many people request keys. But this can be solved because we can request a high volume of keys to put in memory. That's no problem. We can lose keys if a Redis server goes down. So let's see. What are the trade-offs you always have to make for a distributed system? So there's this is kind of a distributed system, but it still has like a single source of truth, the KGS, which, yeah. I'm thinking like what are analogs to other services which have this problem, but we basically have an append-only service. So we never have to resolve conflicts. We have append-only, what's the word for it?
Okay. So yes, that's good. So just going to end the interview. Before that, I want you to tell me about the HTTP status codes that you are going to return. If it's the connection is invalid or if your service is down. So how are you going to do the exception handling, or how are you going to return return the status codes to the user?
Okay, so oh god, I don't remember all of my status codes, but if something goes down, it should have a hot failover. Everybody has a hot failover this, so I'm not anticipating throwing any 504 records. Of course, you eventually can. If everything goes down, you can throw 504 records. Let's say somebody's used all the IDs of the Redis cluster. If someone has used all the IDs of a Redis cluster, you can either return resource unavailable, which is
okay.
But you can either return that, or you can just have them wait for the next one while Redis queries more. We have internal service failure, but since the client isn't requesting, currently we're not asking the clients to limit their request. So the client is never going to get like what's it called? What are they called? 400 is when the client sends bad days. So the clients will never see a 400 HTTP status code because we're currently not asking for rate limits, or they're not giving us any information. So we could have like 500. So I don't remember exactly my 500 codes, not precisely, but we could have a 500 in case our services actually go down and there's no backups. And maybe if we want them to know really quickly whether or not they have an ID or not, we can send a 300 like resource temporarily unavailable if we run out of keys. Does that satisfy your HTTP curiosity?
Yes. Okay. So I think that's good. So
thank you. It's a 1 hour. It's quite long.
Yep. Okay, sure. So I already did the annotations. Okay. I'm going to in the interview. I'm going to put out some feedback for you then. Okay.
Thank you very much. This is extremely useful.
All right. We'll see you then. Bye.